Gravity is a fundamental force of nature. It is what keeps us grounded on Earth. It is the force that causes objects to fall to the ground. Gravity also holds the moon in orbit around our planet. We often take gravity for granted. It is an invisible force that is always present. Without gravity, life as we know it would not be possible. Gravity is not the same everywhere on Earth. It varies slightly from place to place. This is due to several factors, including the Earth's rotation and the uneven distribution of mass within the planet. Scientists are constantly studying gravity to understand our planet better. By measuring these variations, scientists can learn about the Earth's structure and composition. In the vast expanse of the Indian Ocean lies a fascinating anomaly, a region that has puzzled scientists and intrigued researchers for decades. This region, known as the Indian Gravity Hole, exhibits a weaker gravitational pull compared to other parts of the Earth. It is a place where the force that keeps us grounded is slightly less potent. This intriguing phenomenon has captivated scientists and sparked curiosity about the hidden workings of our planet. Researchers from various fields have come together to study this anomaly, hoping to uncover the secrets it holds. The Indian Gravity Hole is not a physical hole in the ocean floor. Instead, it is a region where the gravitational force is slightly weaker, creating a unique environment that challenges our understanding of Earth's gravitational field. It is a region where the Earth's gravitational field is slightly weaker. This subtle difference in gravitational pull can have various implications for both natural processes and human activities in the area. This means that if you were to stand on a scale in the Indian Gravity Hole, you would weigh slightly less than if you were standing on a scale elsewhere on Earth. The difference might be small, but it is significant enough to be measured and studied. The existence of the Indian Gravity Hole was first discovered by satellites. These advanced instruments orbiting our planet have provided invaluable data that has led to the identification of this gravitational anomaly. Satellites are used to measure the Earth's gravitational field with great precision. By analyzing the data collected from these satellites, scientists can map out variations in gravitational strength across the globe. When scientists analyzed the data from these satellites, they noticed a distinct dip in the gravitational field over the Indian Ocean. This dip, now known as the Indian Gravity Hole, has become a focal point for further research and exploration. The discovery of the Indian Gravity Hole has raised many questions. What causes this weaker gravitational pull? How does it affect the surrounding environment? These are just a few of the questions that scientists are eager to answer. Scientists are still trying to understand why the gravitational field is weaker in this region. Through ongoing research and collaboration, they hope to uncover the underlying mechanisms that create this fascinating anomaly and what it can teach us about our planet. The Earth is not a perfect sphere. It bulges at the equator and is flatter at the poles. This uneven distribution of mass affects the Earth's gravitational field. The Earth's rotation also plays a role in gravity variations. As the Earth spins, it creates a centrifugal force that pushes outward. This force is stronger at the equator and weaker at the poles. The combination of the Earth's shape and rotation means that gravity is slightly stronger at the poles than at the equator. This difference in gravity is very small, but it is measurable. Other factors can also affect local gravity. For example, mountains have more mass than valleys, so the gravitational pull is slightly stronger near mountains. To understand why gravity varies across the Earth, we need to look beneath the surface. Gravity is not uniform everywhere on our planet. It changes depending on where you are, and this is due to the complex structure of the Earth beneath our feet. The Earth is made up of different layers, each with its own density and composition. These layers include the crust, mantle, and core, each playing a crucial role in the gravitational variations we observe. The Earth's core is the densest layer. It is incredibly hot and composed primarily of iron and nickel, which contribute significantly to the Earth's overall mass. It is made up of iron and nickel. These heavy elements create a strong gravitational pull, affecting the gravity we experience on the surface. The mantle is the layer surrounding the core. It is composed of semi-solid rock that moves slowly over time, driving the movement of tectonic plates. It is made up of hot, dense rock. The mantle's movement and its varying density also contribute to the gravitational differences across the Earth's surface. The crust is the outermost layer. It is the thinnest layer and is where we live, build our cities and grow our food. It is the thinnest layer and is made up of rock, soil and water. Despite its thinness, the crust's composition and structure vary greatly, influencing local gravity. The variations in density and thickness of these layers contribute to the uneven distribution of mass within the Earth. This uneven distribution is what causes the gravitational field to vary from one place to another. These variations in turn affect the Earth's gravitational field. By studying these differences, scientists can learn more about the Earth's internal structure and composition. Scientists use a variety of techniques to study the Earth's interior. These methods help them map out the different layers and understand how they interact. These techniques include seismic waves, gravity measurements, and magnetic field studies. Each method provides unique insights, helping to piece together the puzzle of our planet's inner workings. Section 5. Mapping the invisible satellites and the geoid. Scientists use satellites to map the Earth's gravitational field with incredible precision. These satellites orbit the Earth and measure subtle variations in gravity. The data collected by these satellites is used to create a model of the Earth's geoid. The geoid is a representation of the Earth's shape if it were covered entirely by water. The geoid is not smooth like a perfect sphere. It has bumps and dips that reflect the uneven distribution of mass within the Earth. The Indian gravity hole is one such dip in the geoid. By studying the geoid, scientists can learn about the Earth's internal structure, plate tectonics, and even ocean currents. Section 6. The Indian gravity hole, a deep dive into the anomaly. The Indian gravity hole, a prominent dip in the Earth's geoid, has been a subject of intense scientific scrutiny. This anomaly, located in the Indian Ocean, has puzzled scientists for decades. The geoid, which represents the shape of the Earth, shows a significant dip in this region, indicating a weaker gravitational pull. Several theories attempt to explain the weaker gravitational pull in this region. Researchers have proposed various hypotheses, each offering a different perspective on the underlying causes of this anomaly. One prominent theory links the anomaly to the presence of a massive plume of molten rock rising from deep within the Earth's mantle beneath the Indian Ocean. This plume, known as a mantle plume, is thought to be a significant factor in the region's unique gravitational characteristics. This plume, known as a mantle plume, is believed to have lower density compared to the surrounding mantle, resulting in a weaker gravitational pull in the region. The mantle plume theory suggests that the rising molten rock displaces the denser material around it, creating a localized area of lower gravity. Another theory suggests that the Indian gravity hole is a remnant of an ancient subduction zone. Subduction zones are areas where tectonic plates collide and one plate slides beneath the other, often leading to significant geological changes over time. Subduction zones are areas where tectonic plates collide and one plate slides beneath the other. This process can create areas of lower density in the mantle, which can persist for millions of years, contributing to the observed gravitational anomaly. This process can create areas of lower density in the mantle, which can persist for millions of years. The remnants of these ancient geological processes continue to influence the Earth's geoid, providing valuable insights into the dynamic nature of our planet's interior. Understanding these anomalies not only helps us learn more about the Earth's past, but also aids in predicting future geological events. Section 7. A dynamic planet, Earth's ever-changing gravity. The Earth is a dynamic planet and its gravitational field is constantly changing. These changes are influenced by various factors, including geological processes, the movement of tectonic plates, and even the melting of glaciers. Geological processes such as volcanic eruptions and earthquakes can redistribute mass within the Earth, leading to localized changes in gravity. The movement of tectonic plates, which are constantly shifting and colliding, also contributes to these variations. The melting of glaciers, a consequence of climate change, is causing a redistribution of mass from the continents to the oceans, further impacting the Earth's gravitational field. Section 8. Unlocking the secrets. The quest for answers continues. The study of Earth's gravity and its variations is an ongoing endeavor. Scientists are constantly developing new technologies and methods to improve our understanding of the forces shaping our planet. Advanced satellite missions such as NASA's Grace-4 continue to provide valuable data on Earth's gravitational field, allowing scientists to monitor changes with unprecedented accuracy. Sophisticated computer models are being developed to simulate the complex interplay of factors influencing Earth's gravity, aiding in the interpretation of observational data and the testing of scientific theories. Section 9. Gravity's grip: implications for our world. Understanding Earth's gravity and its variations has profound implications for various aspects of our world. From unraveling the mysteries of our planet's interior to predicting the effects of climate change, gravity plays a crucial role. Precise gravity measurements are essential for navigation, resource exploration, and monitoring groundwater levels. By studying gravity variations, scientists can identify areas prone to earthquakes and volcanic eruptions, aiding in hazard assessment and mitigation. Furthermore, understanding the impact of melting glaciers on Earth's gravity is crucial for predicting future sea level rise, a critical concern in the face of climate change.